Just welcome everyone for our talk Tuesday. Today we have Dr. Steve Guimond, who's at Hampton University as a tenure track faculty member now, but most recently he was also an associate research professor in the Department of Physics at UMBC. And he's has a lot of background and related work to iHARP, but his most recent work focuses on wildfire smoke plume modeling, which I hope he'll be talking more about today. So with that, Steve, please carry on.
Yes, so this is just a teaser title. I'm going to talk about something totally different after this. So. But no, thank you. And I appreciate the invite. I'm sorry I didn't get to connect before I left. Actually, the job situation changed pretty rapidly for me, so I had to kind of move fast. But yeah, this is some work I had done over this past year on wildfire smoke plumes, and it's been a very timely topic, as you can hear about in the news. The fires in Hawaii have been very devastating, and so they're becoming more common. This is a work that was done in collaboration with Los Alamos National Lab. So Los Alamos National Lab is a national security lab. Their main focus is nuclear weapons and their effects. And so they are using this wildfire as sort of a surrogate for understanding what would happen if a nuclear weapon went off and what would the climatic effects be of that, the so-called nuclear winter. So I did this work in collaboration with John Reisner and Manvendra Dubey from Los Alamos. And then I had some questions on I use the GEOS NASA model for this, and I want to acknowledge my people who I asked many questions to on that. So next slide. So yeah, I just mentioned the Hawaii fires that I'm sure all of you are familiar with in the news, but there's been a lot of these large, intense fires, which is kind of what we classify as a megafire recently in the past several years. And that's, of course, a consequence of climate change, that, things are getting drier and warmer, especially out west. And then there's also been a number of years where there haven't been any fires. So there's just a lot of fuel and debris on the ground that is collecting. And it's just really ripe conditions to excite these really large, intense wildfires. So here's the ones that have been published most in the literature and studied most are this British Columbia event in 2017 called BC17. These are just some pictures from Wikipedia I took of the fires along here. This is a visible satellite image showing the red shows the active fires, and then obviously the white is the smoke plumes from that. So you can see many active fires along this mountain range here, and then they can combine and to form very large smoke plumes that can then rise very high in the atmosphere. In Australia, 2020, which I think is what Sudip was mentioning, was the ones in Australia that were very large, and just devastated this region. You can see effects of these. Here's a nice image from space where you can see these smoke plumes just dispersing throughout much of the the southern hemisphere here. So they've done a lot of devastation there. We'll continue to do that. We want to understand more details about what their climatic effects may be. Certainly the fires themselves are devastating, but what happens after when the smoke plume is been formed and it rises? Does that play any role, and how can we understand that better? So I talked about these things transport a lot of the smoke upward. So after the fire is started, you have these very the fire starts, of course, because you have very dry and very warm conditions at the surface. You might get a lightning strike to initiate something like that. And then you get that fire, and you have these very large smoke plumes that are coupled to convection. So these pyroconvection cells have a very strong updrafts that can transport a lot of that smoke upwards in a very short period of time. The formation of these pyro-CBs are due to the surface buoyancy just from the fire itself. It serves as a buoyancy source. There's dynamic forcing. You might have a front approaching the area that serves as a trigger for that. In addition, there is some moisture still, even at the surface, though it's very dry. In the mid-levels to form that cloud, you have some moisture source there and additional instability to kind of further, extend that updraft aloft. And then they once they reach the tropopause, if they're strong enough, the updrafts can penetrate the tropopause, and then you can get the smoke in the stratosphere. And of course, once you can get it up there, you can transport it long distances from the jet, very strong winds up there. and there's really not much weather, at all to rain out. All you're above the rain, and so you can't really rain it out, and it can stay up there for many months, up to a year. And the question is, what's the effect of that long term, and how does it, affect local and regional climate as well as global climate? These piracy bees are very small in scale, maybe 10 kilometers wide. So with current climate models that, we can run them high resolution, as I'll show, but for ones you want to run for very long periods of time, you might run them at 1 degree, 2 degrees, and those obviously cannot be directly simulated. So we have to do some, kind of fake sort of things to get them in there to the model, and then parameterize them in a very crude way, which is not very good. The other way that you can get smoke aloft is through this self-lofting process on the right. So what happens is the smoke, most of the smoke that comes off of fires is organic carbon, this white smoke, but there's a small fraction that's black carbon, and of course it's black, and can absorb very strongly. The radiation can absorb very strongly out of that, which provides another buoyancy source on top of the convection to further lift it. It's much slower lift rate, but it's more widespread as opposed to these isolated cells. And so we feel that the main way to get it up there is through the piracy bees. That's the strongest way to penetrate. Here you can kind of see a convective cloud where it's sort of, you might take this outer edge here as the tropopause, and it's sort of penetrating up through there. But then once it's in the stratosphere, it can further rise from this self-lofting process to very high altitudes. And the higher you get it, the harder it is to get it out of the stratosphere. So the climate effects, previous work, as I showed that these can spread very long different distances because it's in the stratosphere, very long lifetimes, and it's just the only way it can get out really is through mixing and the settling process, which can take quite a while. The climate effects of these is highly variable. The TOA radiative forcing for this BC17 event was fairly small, I would say. It was a cooling effect of only like 0.03 watts per meter squared. So that's fairly small. And for bigger ones like the Australia event, though, it can be more significant. So this is, an order of magnitude larger, but still cooling effect, as shown in this paper here. So the jury's still out kind of on some of these calculations. I know that there's some different ways you can calculate TOA radiative forcing, but we'd be curious to look at the Hawaii fires to see where they land. And but some of these more extreme ones can be are on the par with moderate volcanic eruptions, which are known to play a role in climate. So they can have an effect. It's just the more extreme ones are obviously the more significant ones. So here's the BC17 event from this paper showed this is the LiDAR backscatter, and you can see where this initial injection is where the piracy bees generate or transported all that smoke upwards into the stratosphere, and then there's sort of a long extended impact or a tail of decay out of there from the settling. So that takes several months, and so LiDAR is a very good instrument to be able to monitor these and use that data to plug into models. As I mentioned in the beginning, the analogy that why Los Alamos is interested in this is because of the nuclear winter problem, where this was studied back in the 1980s initially, I believe, where they had identified where if you had, two countries exchange nuclear weapons, you can generate a large smoke plume, much of which could be black carbon, and it would rise high into the atmosphere, block some of the incoming solar radiation, and cool the Earth, and therefore it was called nuclear winter, which would destroy all the crops, and you would have a global famine. So this has been kind of revisited recently with improved models and understanding of this. And they were doing a scenario, and this is published in the literature, of say India and Pakistan had a nuclear exchange, what would happen? I ran a quarter degree, and GEOS, for those that don't know, is the climate model at NASA, specifically coming out of NASA Goddard. It's the model where they use a lot of satellite data and other things to simulate weather and climate. But I ran it at a quarter degree, and if I let this play back out, you can see I generated these smoke plumes that were sort of, I had to get some information on what a nuclear weapon would produce, and there's some rough estimates of that, but I'll let it play back, but I released it over the India area, and then it pretty quickly it rises high into the atmosphere. And this is at 50 millibars, so pretty high in the stratosphere, shows that it would spread over much of the globe in a short period of time. So there it is. It blows up, and then it kind of spreads very quickly over a period of maybe 2 weeks over the globe, mainly in these mid-latitude belts here where the strongest winds are. So this was just an example of how the wildfires are natural analog to this, and they wanted to use them to study, well, how does the smoke rise and what's its climate effect? So the broad goal of this project was to analyze regional global climate effects of megafires. The specific goals that I'm doing is to understand how the dynamics controlling this transport, the vertical transport, and the concentration of the smoke plumes and how they move across the globe, to understand the characteristics of the smoke plumes. A lot of times we want to know what's the concentration of the black carbon in these smoke plumes. It's usually pretty small, but it's a critical amount. So maybe only 1, 2, 3%, but it's very sensitive to that number because of this self-lofting effect and the absorption of radiation and buoyancy that can lead to a high injection heights. So we're interested in the total mass, and then how the breakup into the BCOC fractions, the lifetime it resides in the stratosphere, and then how you would place this into the model. Since you can't simulate these pyro-CVs individually, where would you inject the smoke based on observations? And that really depends on how long it can last in the model. So usually what people do is they use satellite data itself alone, or with models, of course. It can be hard to just use the satellite data because you don't have the predictive capability to test that, but the model is used to understand and tease out certain features of the transport. There's large uncertainties with several of these things. With satellite data, there's assumptions they make for retrieving certain things about BC and OC, as well as their interactions. Models have many uncertainties, as you might be aware of the resolution and the parameterizations of models, and how do these things interact to produce the result we want. So again, I use the GEOS model, which is the model from NASA Goddard. I gave this talk to the GMAO, which is the modeling group there, so you won't need to know some of these things, but I'm using an atmosphere component only. They have a coupled model to the ocean, but we don't really need that for our study. And my goal was to look at this at very high resolution and compare it to what people are typically using. So people typically use about a 2 or 1 degree spacing of the grid cells across the globe. And I've gone down all the way to 7 kilometers, including a nonhydrostatic simulation. So that just means we're explicitly calculating the vertical accelerations, whereas everything else is run hydrostatic, where it's all implicitly balanced in there for the vertical transport. So that was an important thing to look at because vertical transport, as I showed, is an important metric for how high these plumes get. So that you're not going to need to know. There's the aerosols is an external mixture using a simple model that has bins for just a few different variables. One for the 2 ones I focus on, of course, are black carbon, organic carbon. And then there's some specifications you can put in for the radius of the particles and the density, and these are listed here. There is some sensitivity to these as well, and that's another tuning knob in the model that we try to back out. But I've try to focus on only a couple tuning knobs so that we can keep the problem tractable. I don't have any interactive chemistry. There is some chemistry effects that can happen in the stratosphere, but I've kept that simple setup so we can just focus on the kind of resolved dynamics. And the initial conditions are real initial conditions that come from this Mirror-2 reanalysis data that has real meteorological fields in it. And it's done 3 days before the wildfire plume event happens. And I'm focusing on the BC, British Columbia event in 2017. So I initialized these fields 3 days before the wildfires occurred. And then I input forcing into the model, which I'll describe next. So as I mentioned, you can't get these plumes, these wildfire plumes in the model directly because of the resolution. So people have to initialize them ad hoc. And what we did is we followed a paper that was published in 2019 in GRL for how to, to use a kind of a baseline what the community has been using. And so what we did is we said 0.2 teragrams of smoke mass was initialized at a high altitude. This is above the tropopause here, just above, or actually a little bit above the tropopause at this altitude, at this British Columbia latitude. And so we did it that way. That was based on LiDAR data where you can see the smoke plumes, and they kind of estimate the amount of mass of that, which is uncertain. And then the rest of this 0.2 teragrams was also spread evenly below in the stratosphere or in the troposphere, just to kind of track in the lower levels of where the smoke is moving. Now, of this mass, 98% of it was specified as organic carbon, 2% was the black carbon. So that's been sort of in the literature, this kind of ratio of the BCOC has been kind of not really agreed upon, but sort of more common, I would say. And so we use that as a baseline. And then we inject the smoke for 5 hours. And that's kind of the lifetime of this event that we had. So it started on this date at this time for 5 hours. Then on the 13th of August, it shut off. The smoke forcing shuts off, and then the model freely responds to that forcing. So I did this at 4 different resolutions. The first one is at 2 degrees. At 2 degrees, people had just initialized one grid point, one single grid cell with this profile. So it's just one vertical profile. Then what I did is to get a similar smoke spread, I divided up that amount of mass at an increasing resolution and got the same spread, but it's just spread over more grid points. So for the 1 degree simulation, it's spread over 4 grid points, the same amount of mass and the same spread. So there's not like a ball of smoke in the center of a higher degree run. It's just spread out evenly over that same 2 degree area. Okay, so then when you go to a 1/4 degree, you get 64 grid points within this 2 degree area spread out with that smoke. And then at the 7 kilometer, here's over 1,000 grid points that you have. And this is just kind of what it looks like at the 1 degree. You see it's kind of an oblong shape. Here's 4 grid points. And I made sure that this is all numerically accurate. So I integrated this in the model in the model native coordinates. Because the model runs in this cube sphere grid, and it's not really a lat long grid. So I did that on the native model grid, and that's what it looks like at 4 grid points. When you resample it to the higher resolution, it looks more well defined at this 1/4 degree with 64 points. So they're all the same amount of mass is getting injected. It's just spread out evenly over the same area with more points. So it gets us some results of these tests. And the summary metric here is the stratospheric lifetime. So this is just an integration of the total smoke above 150 hectopascals, which is taken to be the tropopause level at this latitude. So we just integrate all the smoke mass, and we're looking for where does this number fall off to 1 over E, and that's kind of our E folding time. Where we can tell the time and days of where this stratospheric lifetime is occurring. So this is pretty typical way to calculate it. In observations, people identified about 5 months for this event from several papers here. So we're kind of using that as a somewhat of a guide, but we're also using because we don't really know, a lot of these papers have used different heights for their injection and maybe a little bit different total mass. We also run a 7 kilometer reference simulation. So that's our high resolution reference. And then we compare the exact same specifications at these coarser resolutions to that reference so that we're all consistent. And the 7 kilometer reference gives about 6.9 months. The reason why it's longer than the observations is probably because we're using too high of an injection height. As I mentioned before, it was at 13.5, and that was just based on this paper. You can adjust that, and it's an uncertain thing you have to pick out from satellite data, but that can be adjusted. So it's more appropriate to use, if you just want to compare the resolution, to do the same thing for all the changes in resolution. Okay, so when you do the like the non-hydrostatic, it's pretty close, 6.8 months. So it's a pretty small difference in there. So maybe the non-hydrostatic effects are relatively small at this for this problem. But then if you go and look at what people are normally doing is about 2 degrees, maybe 1 degree, and you can see that it drastically underestimates what the reference is here. So you're only getting about 3.5 months from a 2 degree. It's about a 50% reduction in the lifetime. And then if you go to 1 degree, you're getting, closer, but still a 15% difference. The 1/4 degree we said was pretty close to the reference. It's only about a 4% difference. And so we can kind of say from this, if you're using about a 1/4 degree resolution, you're sampling that plume well enough that you're getting pretty close to the reference. And so you don't necessarily have to go down to 7 kilometers to resolve this plume, but you need to go to at least a 1/4 degree. And if you're going to using 2 degrees, you're going to really underestimate the effects of that plume. So this shows you that you can get the right result for the wrong reasons in the model. And this is sort of an issue that I'll get on in the conclusions here, but that just gives you an overview of these simulations, and I'll get into some details now. So here's the smoke structure at early times, about 6 days into the simulation, and I've shown these pictures are averaged over longitude, and so I'm showing them as a function of latitude and pressure or height at the different resolutions. So it's kind of a zonal mean picture at these different resolutions, so you can compare. The red line is the tropopause height as a function of latitude. And so, here's at the 2 degree, you see the smoke plume concentration is just above 15 kilometers height. But if you look at the 1 degree, it's a bit higher, maybe 20 kilometers. The 1/4 degree, it's much higher. I would say, it's hard to tell based on these individual plumes, but maybe centered at 25 kilometers height. And then the 7 kilometer, it's actually probably around there or slightly lower. So you can see where there's quite a bit of variability, especially in these coarse resolutions. And I'll get to the reasons for why that is occurring, but this shows you why you get a shorter lifetime. You get a shorter lifetime in the 2 degree because it can only rise a very small amount, only a short amount of distance into the stratosphere, whereas these other resolutions are rising very high, therefore it takes longer for them to settle out. And so you can see that from these comparisons relative to the reference, the peak heights is only 40% lower than the reference, so it's much more reduced in the 2 and 1 degree. And the 1/4 degree is again pretty close, about 6% too high relative to the reference, but still within an error tolerance there. Here's 10 days later at 16 days. You can see what's interesting here is if you compare the 2 degree, it really hasn't changed a whole lot in another 10 days here. It stayed almost at the same height. It's dissipated a little bit, but these other ones have risen higher. You can see that the 1 degree seems to be rising much higher at this time. The 1/4 degree, this is at 30 kilometers. Some of the smoke is above 30 kilometers, but it's maybe centered much higher than previous. And then the 7 kilometer is also risen as well. And so here's again these numbers showing the dissipative effect if you use these coarse resolutions, whereas the 1/4 degree is kind of approximating the reference fairly well. So there's still quite a bit of rising going on, even greater than 2 weeks past the end of the fire event. And here's what it looks like. This is column integrated total smoke mixing ratio at 6.2 days. So this is comparison to the vertical cross section. This is a horizontal. And it just shows you, this is only short times into it. And so you're not going to see too many differences here. But, as I move forward, you'll see some bigger differences. You can see the breakup of the plume, of course, as you go to higher resolution. At the 7 kilometer, you can break up into small, discrete pockets of smoke. And it's sort of been stretched a little bit into Europe here. It's a little bit more stretched that way and dispersed at different altitude or higher latitudes in the 7 kilometers. But at this early time, they look reasonably close. As you go to 16 days here, they look quite different. So here's the 2 degree. You can see it's a very diffuse, kind of stretched out smoke. It's not very concentrated. And the 1 degree, you do have a pretty well-defined ball of smoke here over the Great Lakes region. And then in the 1/4 and the 7 kilometer, there's different placements of that ball. So it's well over the northern latitudes here, and then actually the 7 kilometers rotated back around the globe into the central U.S. here at this time. So the horizontal and vertical and this is again the reason for this horizontal difference is really due to more of the vertical lofting difference. So these are at different heights, and therefore the winds are changing quite a bit with height, and so they can transport the plume and the smoke at different horizontal locations. So now I get into a little bit of why these coarser resolution model results don't are having this dissipative effect. And the way to analyze this is by looking at the kinetic energy in the model and the spectra. And so we want to look at the energy as a function of scale in the model to see, what's more accurate and where you're dissipating energy and where, you're gaining energy. So what I've done is computed the horizontal kinetic energy spectrum per unit mass as a function of wave number. Basically, the zonal and meridional winds are decomposed in latitude. So you're around, it's naturally periodic. You can perform an FFT on that and calculate the energy spectrum pretty easily. I've averaged the spectra over the smoke region that's most active. So that's 40 to 70 degrees north, like a 30-degree latitudinal band. And then I've averaged it over a good chunk of the stratosphere, 150 to 10 hectopascals. So that gives you a bulk measure of the kinetic energy, and we can look at this in the different resolutions and see how they're approaching the reference one. So we know from theory and observations that we have a slope of the energy where we think is correct. It has a slope for the wave number to the -3rd power in the large scales and a -5/3 in the mesoscale. So I'll show you how that may be validating with these runs. So here's an example for 6 days into the simulation of the various resolutions. What I've put on here are these reference lines. This dashed black line is the -3rd theoretical and observational slope of kinetic energy at large scales. So these actually get you oriented on the figures. This is the wavelength of features on the x-axis in the model, and this is the kinetic energy density along the y-axis, just how much energy per unit wavelength. So here, and then the purple line here is the mesoscale, where it sort of shallows out into this transition into the mesoscale region here. So all these different lines correspond to the different runs I did. The 2 degrees here is in blue, and you can see that if we're using these black lines as the reference, you can see that it falls away from the black line pretty fast at about a wavelength of, well, this is 1,000 kilometers, so it's about 10,000 kilometers here. So at about 10,000 kilometers, it really starts to drop, and it's well below this black line, which we would expect. So that means that there's less energy in the model at these scales. And this P here represents the scale of the smoke plume that I initialized in the model. It was a 2-degree smoke plume, but you represent that as in the model here as this wavelength. And so it was only initialized at 1 grid point, which is right at the edge of the resolution of the 2-degree, because that's only 1 cell there. And it's very dissipative. You can see at this point, the energy is several orders of magnitude below the black line. So what that means is that I'll get to in a second, but the kinetic energy associated with that initialized plume is very weak. It's very dissipative. And that's not going to allow for a correct transport as well as in the horizontal as well as in the vertical, because of the way the vertical is computed in the model. So if you look at the 1 degree, it's better. It's much better. It's about an order of magnitude better, but it's still below this black line. But as you go to the 1/4 and 7 kilometer, they're agreeing very well with this black line. And so we would say these are well resolved. The plume that was initialized is well resolved. We're getting good kinetic energy that's agreeing with theory, and therefore your plume transport and it should be more correct. And then you can see that even the red and the green lines start to decay at some scale. This is just at any model, whatever resolution you choose, there's going to be this decay. The higher resolution will just keep pushing this decay further and further to the right. So you don't necessarily need to go to 7 kilometers if you're only caring about resolving the scale. You just need it to be well resolved at this initial, kind of scale you've put it in. And that's really at the green line here, is 1/4 degree is matching pretty well with both the black dashed line and the red reference line here. And so that comes out to be about 7 to 8 times the grid spacing. That's the kind of resolution you need to sample the plume correctly. So with that with that knowledge that we know the quarter degree is well resolved, I took that and I said, okay, now let's start, now that we know the dynamics is accurate at a quarter degree, let's start changing some of the other uncertainties in the model to get a better handle on what's matching the observations. So we found the initial injection height is too high. That was, that 13.5 kilometers was too high. It was producing too long relative to the observations of about 5 months. So we did some perturbation runs, and these perturbation runs are shown here where we changed the injection height. So here's the control, 13.5 kilometers injection. Here's the mass and BC fraction and these different grid spacings. So with a quarter degree, I reduced it to 11.5 kilometer injection height with the same mass and same BC fraction. Well, that produced 4.4 months, which is a little bit too low relative to the 5. And that's shown, I believe, in this figure here. So this figure shows time in days as a function of pressure and height averaged. And you can see that the smoke, is a little bit too low in the in terms of altitude, in terms of its timeline. So the next perturbation was we raised it to 12.5 kilometers and kept everything the same. That produced a little bit too high, 6.3 months. Here's that same figure. You can see the smoke rises too high, and then it takes longer to settle as well. The third perturbation was we ran 12.5 kilometers, but then we changed the BC fraction. So you can also change the mass, but we said you have to sort of fix one of these. Otherwise, you just have too many degrees of freedom. But we kept the 0.2. We said that's probably a reasonable mass based on other studies, but this is an uncertain fraction, the BC fraction. So we reduced it to about a half or 0.75. And using the same quarter degree, and we get about 5.1 months. So that's very close to the observations. And most of the observations we're showing from these other papers about a 12-kilometer injection height. So because of the model grid spacing, we had to do 12.5. It was only about like coarser. We couldn't get to exactly 12. So we sort of inferred that you need to go down to about 0.5% in BC fraction at 12-kilometer injection height with this same mass and a quarter degree to match observations. So that was sort of our optimal run. 12-kilometer height, yeah, I wrote it down here. Well, I say 1%, but I think that's a little bit lower. Oh, I'm sorry, I take that back. This half was because we raised it at 12.5. When you go lower, you actually have to raise the BC percentage because that's going to add more lofting. So yes, we came to the conclusion that 1% BC, 0.2 teragrams of mass, and 12 kilometers height is more our optimal setup for this problem. So how am I doing on time here?
I think we're good for time.
Okay, so the second part of this, and this won't take as long. This is I want to understand the vorticity dynamics associated with these plumes. So my main research is on hurricanes, and so I'm very interested in swirling flow. And so it's been reported that a lot of these smoke plumes form anticyclonic vortices with them. So I want to understand, how does that occur? It's been documented they produce that, but no one's really shown how does that occur. And so I wanted to take the model data and understand that. And what does this look like as a function of resolution here? So this is the vorticity structure at 6 days into the simulation. Here I've taken it within the smoke. So total smoke greater than this value and greater than 150 millibars. So it's above the tropopause. The vorticity was vertically averaged during this time. So that's only within the smoke. And this is what it looks like as a function of resolution. So you can see these are the same color bars here. There is a negative vorticity, so anticyclonic spin at all resolutions here. But you can see it's much more concentrated, as you would expect at higher resolution in the quarter and especially 7-kilometer. What's interesting, in the 7 kilometers, you get some discrete eddies sort of breaking this up into smaller filaments, but it's of course very smooth in the other ones. So, but this vorticity, I do with very high Rossby numbers, which is very fast spin. These are pretty slow for me, so they're less than 1. So it's I just characterize that with the Rossby number of less than 1 as a kind of a slow regime. So these are not like rapidly rotating vortices. They're kind of slowly rotating. As you go really far out, in the 2 degree, actually this anticyclonic vortex starts to disappear. it becomes so, it's so dissipated and weak in the model that it just gets stretched out and the vorticity gets destroyed. You can see I can't see any more indications of, I was following the smoke plume along here, and I can't see any more negative vorticity. It's all positive here. And at 1 degree, it's still stretched out. You can see it's not concentrated at all, but it's kind of, very weak. And in the 1/4 degree, you can see it much more prominent as more of a concentrated plume here. And then in the 7 kilometer, it's in here, but it's sort of, the 7 kilometer, you start to get a lot more positive filaments as you get changes in sign of the wind gradients and things, but it's still there for the most part. So the question is, how does this form? How does you get this anticyclonic vortex? So what I did is a Lagrangian relative vorticity budget. So those who are not familiar with that, what this is on the left-hand side is the material derivative of vorticity on a pressure surface. So you're just following, and I'm sort of following the smoke plume. That's what makes it Lagrangian, is I'm looking at the center of mass of the smoke plume and following it around and calculating its vorticity and the terms that describe the vorticity change from the model. So this first term is the stretching effect, where you converge or diverge air. You can stretch and increase the vorticity or decrease it. This term is the beta effect, or the differential rotation of the Earth as a function of latitude. This term actually turns out to be pretty small. So, and then this is the tilting term, which has to do with gradients in the updrafts. And then you have a term here, which is subgrid scale dissipation, which I'll assume small at this level. So the 2 terms that really play a role are the first and the third. That's the stretching effect and the tilting effect. So to look at this, I want to first know what's the background vorticity that this smoke plume is entering. And so this is a plot of the relative vorticity at 150 hectopascals just before the smoke plumes were initialized in the model. So you can see in this black box that the vorticity has a background of negative. But what we're really looking at in this term here, you see it's the relative vorticity plus F, which is the absolute vorticity. And the absolute vorticity is all positive, because the Coriolis parameter is pretty strong at these higher latitudes. So it's actually all positive absolute vorticity here. So that term is positive, which makes this negative out in front. And then the convergence really determines, or divergence determines the sign. So here's these 2 terms that are most important. Here's what the vorticity looks like of the plume at 5, this is 5 hours after the 5-hour injection of the smoke. So here's the vorticity, anticyclonic. Here's what the divergence looks like. So it's positive here, and then all these other, the tilting tendency is pretty small. I'm sorry, this is the divergence inside here, which is positive, but with the negative, the stretching tendency is all negative there. So you get diverging air at the top of the updraft, which is why that's positive. And then you have the absolute vorticity, multiplied in through there with a minus sign. That's what gets you this negative stretching tendency term. And so that's what the total material tendency is a function of. Okay, so I'll go through a couple more and I'll explain this physically a little bit more. At later times, a little bit later, you see kind of a similar effect. The tilting term has got some larger effects on the edges, but in most part it's smaller. So it's really the stretching term, and you get some differences in the center of the plume and on the edges, but it's really the convergence and divergence of air stretching or compressing the background vorticity that is generating the changes in vorticity. And then I think I'll skip this for the most part, but it just shows more of the same kind of effect. I think this is later on in the simulation, 21 days. So I will get to what the result of that in the end in the next slide, but the main results of this work, and this actually it's not in review, it's fully published in James. I can send you a link to the paper if you want, but the community, so there's been a paper in Science, which is a high profile paper that used a 2-degree simulation of this event. And they said that, well, we need to use this special chemistry to describe the decay of smoke in the upper atmosphere. Well, what we're finding is that most of these studies are using very dissipative dynamics due to the fact they're choosing coarse resolution in their models, which means that you need some other effect to explain the observed decay or something. So this leads to a problem where you're sort of trying to compensate for your errors in your dynamics by introducing new physical processes. And so that's, needs to be done more carefully by fixing and doing accurate dynamics, and then sort of getting into more of the details of the missing physics in the model. So you really need to sample any feature in a model with about 8 times the grid spacing to minimize your uncertainty in the dynamics. And so these are all these different studies that had used different model spacings. You can see most of them are using like 2 by 2.5 degrees. This one paper was the exception, used 1/2 degree. But some of them have to use very large BC fractions, and that's because they're using very coarse resolution to get their smoke to produce the correct stratospheric lifetime. They need a lot of self-lofting to get that correct. But if you use more of a well-resolved grid spacing, you have to reduce your BC fraction to about 50%. Most people are around 2% here. We find you have to reduce it by about 50% in order to match the observations. So that's the key takeaway from this, is that if you want to improve your model parameterizations and understand the plume better, for the physical part of the plume, you need to have well-resolved model dynamics to do that. And then with the vorticity dynamics, so what's going on, how these are forming anticyclonic vortices, is that you have a background, you have this growing updraft, and then you have at the top of the updraft where that smoke is concentrating more at the top, you have divergence at the top of that updraft, and that leads to a spreading out or a dilution of the background cyclonic vorticity, that positive background cyclonic. That introduces this negative anticyclonic tendency. So that's why it's producing that negative anticyclonic vortex. And all has to do with that updraft, which is not well resolved in the coarse models. When the plume decays, it's just the opposite. As the plume decays, the updraft has convergence at the top so that you get a downdraft, and then that downdraft acts to concentrate the cyclonic absolute vorticity, leading to a tendency near the positive sign. So it will go from negative to positive. So that's kind of the final part of this, is tying together the resolution properties of the model as well as the vorticity dynamics, and that's it. I had some other details here, but this is for people that actually run the GEOS model, and I don't think maybe most of you guys probably don't do that. So that's it. I appreciate listening, and I'll take any questions.
Thank you so much, Steve. I think this is definitely very interesting and intersecting to many of our projects. I'm curious if folks have questions to start off.
I have a question. If I can go ahead.
Yes, please.
Yeah. So I was thinking, like, since at iHARP we look at like polar ice melting, and so the radiative effect of the black carbon is very important. Now, could you please tell us like how the radiative effect of those plumes reaching the stratosphere can affect the ice melting or in the polar region?
Yeah, I mean, so a lot of this it leads to a cooling effect at the surface, only because the radiation coming from the sun is absorbed in the upper part of the atmosphere, and then less radiation, of course, reaches the surface of the Earth. So that could lead to perhaps more ice production over a long period of time. I haven't looked spatially over the globe of where that would be higher or lower, since our study wasn't focused on that. But it's for this Australia event, you see some pretty substantial cooling effects at the surface. So, for example, if you would like, I have my 7-kilometer runs for this archived, and I might be able to transfer some of the data to you for you able to look in those regions for, cooling effects, for example. So I could give you full model output for the very high resolution run, or any resolution I showed here, and you could kind of look at that yourself. But generally there's a cooling effect, and that's what the nuclear winter term came in from, that But yeah, I'd be happy to provide any data for you guys to look at in your specific application.
Right, because I mean, I was thinking like we look at the albedo changes because of black carbon, like they darken the surface and warm the surface and does the melting or accelerates the melting. But on the other hand, when they reach the stratosphere, they also do the cooling. So how these two effects, you know, interacting with each other would be a great idea or great research question to look at. I mean, the data you have is from 2014.
The run I did was for the 2017 British Columbia event, so it's kind of
17.
based on it's sort of quasi idealized because again we had to import. We have real initial conditions. It's just the smoke plume is has to be somewhat idealized because they don't have it in there. But yeah, I agree. There's two effects there, and so what I've focused on is the upper level black carbon source that's leads to a cooling at the surface, but certainly there could be some warming effects if black carbon gets into the ice down low. Yeah.
Yeah, we're thinking like maybe we can look at like the relative importance of the cooling at the top and warming at the surface. How, I mean, if you can share the data, that would be great. I mean, I'll send you an email after this one, after the talk. And
Yeah, sure. I mean, I could start you off with coarser resolution just so you can get a handle on it. And then if you want, so I think most of the smoke, so we're not going to have, in this run, we don't have we could quantify the upper level cooling or the cooling effect from the upper level black carbon, but then maybe you could give me some idea of the warming effect because it's not going to have, all the black carbon gets washed out. And I don't think we have any effects where it like collects, in the ice or something like that. So you might have to use your expertise on the ice part to kind of, look at the two effects.
yeah, we're mainly talking about the spring to summer season because during the winter season when it rains or gets heavy snowfall, not many black carbon rivers we see that time. So mainly say for Antarctica, mainly they come from Congo or Amazon,
Okay.
or for Greenland they come from the US or sometimes from China. So they generally in the spring to summertime when it starts raining or the atmospheric river kicks in. During the winter time we don't see many dry events that time anymore, but for the summer when it melts they are present. So that's why I think we have the like albedo data, surface temperature, radiation data from Series and Morris, and we are looking at that from the data. But I think if we have that data, we can definitely work on that and see how these two effects are, if they're balancing each other or if they're like occurring at the same time or different time, how they're working together. I mean, that would be a very interesting thing to look at, I guess.
Yeah, and it might be, I don't know if there's been any literature on that, but yeah, if not, that's maybe a good way a new topic to explore, especially with more fires occurring and stuff.
Great. Other questions? I also had a couple of questions maybe while folks are formulating theirs. And I'm coming from a very naive perspective because I don't do climate modeling. I do more of machine learning, data science. I guess first a more generic question. You mentioned several different perturbations and, getting to an optimal solution. Are there ways where machine learning could help sort of find the perturbation that leads to the, least uncertainty or finds optimal solutions? I'm sure people have looked at that, but I'm curious what your take is on it.
Yeah, I mean, yeah, there's, I think the useful part maybe would be there's so many nonlinear interactions between these things because if you have, you can change your black carbon percentage, you can change the particle radius. These are all the microphysics of this is very uncertain, and there's some NASA field campaigns that have collected in situ data with aircraft in these smoke plumes to try and better constrain this. So that would be another area to go to help constrain it. But certainly, if you could do a parameter estimation with the machine learning to optimize that, and I don't know how you would do all the nonlinear interactions that occur for multiple things, but yeah, when there's so many tuning knobs in there that can interact, and but if you have a method that can sort of track that better, then that would certainly be helpful, rather than the way I do it, since I'm a modeler and I do other things, but I'm not a machine learning person, so we can just you can run sensitivity tests for over a range and you could bracket it, but if you wanted to really fine tune that, then maybe some more sophisticated methods like you're talking about could be better. But yeah, if you have some, do you know any other machine learning methods good for these nonlinear interactions?
I think for parameter estimation, there could be different types of machine learning methods. I remember, maybe I'm putting Andy on the spot. At some point, we were talking about the modeling that Andy does, and what could be ways to estimate parameters in that. I think Shashi and Andy may have had these conversations, but there could be, right, Andy? I think maybe, I don't know if you want to comment on what you have explored as well.
Oh. Yeah, you're putting me on the spot, like off the top of my head. That's fair enough. I think it might be possible. We've played mostly with Bayesian Monte Carlo, Markov chain Monte Carlo methods to do parameter estimations. I've closely collaborated with a colleague who's the expert in the Bayesian method. So from my perspective, I think we can apply that, but I don't have the deep enough knowledge to figure out, which method exactly has to be used to make it worthwhile. But
yeah.
I see potential there for sure.
Yeah, and again, I apologize. I didn't mean to put you on the spot, but I just remember the conversation. But at the same time, I think to what Steve was alluding to, the different parameters in the model, if there are ways to identify optimal values, because typically when we do machine learning, through the iterations, we have a cost function. And as the cost function decreases, we say that this model set of parameters is the best model. So I think if we can condition it on a cost function of uncertainty, let's say, there could be ways by which, let's say, if there's a cluster of solutions, we find the solution which produces the best outcome. So there could be variations if there are all types of potential solutions. So I was curious if people have looked at that. And also alluding to your comment about the size of the black carbon or the mass to some extent, things could be different, I assume, right? Because if you're talking about wildfires versus volcanic ash versus nuclear, explosion, things could be different and the plumes could be different. So there could be a lot more variation there as well.
Yes, for sure. And yeah, we just focused on one event, and I think the main part of this work is just illustrating because we sort of already knew, like, you have to well resolve things, but what we found in this community of the smoke plume community was that they're using very coarse resolution and trying to do all this parameter estimation and tuning with a coarse model run, and that's just you're sort of you're fighting against the errors in the dynamics of the model, and you could have, it's not really, if you have great data, you want to be using well resolved simulations to be able to take advantage of that data. It doesn't do you any good to use great data and great methods for machine learning on coarse resolution data, because simulations, because you're fighting a bigger error. It's like the elephant in the room versus like the mouse, maybe a baby elephant for the microphysical uncertainties. But but it's somewhat easier now with computing power to run at a fairly high resolution for shorter periods of time, where you can do that. And then once you fix that, then you can start playing the games where so like, for instance, we might run quarter degree with some machine learning to optimize the parameters. We wouldn't want to run that at 1 degree or 2 degrees because it would be a waste of our time. So that's the kind of thing that we might be able to do something there. Yeah, it takes computing, but I think computing is making progress where we can do these things at better resolutions now. So
Great. I see Andy's hand up. Maybe he wants to add something too.
Oh yeah, I really enjoyed your talk, Steve. I think it's been since grad school the last time I saw like a potential vorticity equation in my meteorology classes, and I've always tried to keep, close to atmospheric sciences. But having said that, I remember talks or like papers coming out from the DoD people at Los Alamos with E3SM that have been working on auto calibration in their models, like parameter calibration, but more or less fully automated, where they, I think, set up the model, run it, then automatically, then build statistical surrogates model, and then use the surrogate model to calibrate the parameters. From what I remember, I think it's all in very early stages, so I don't know whether it's working. And I haven't talked to the GEOS people whether they have like similar plans or maybe are already working on these kind of capabilities.
Yeah, it's a tough problem. I mean, these you kind of want to these scale aware parameterizations that are kind of, and it's the same thing with turbulence, is that you want you don't want to have to tune your turbulence model based on what grid spacing you run your model at, right? You want it to adapt to whatever you're doing, and it's a tough problem, and that is a good place for machine learning. I mean, there's people that do that for turbulence modeling, machine learning, and using LES results to calibrate the model parameters for coarse running models and things. So I don't know if you're familiar. There's a project called Climate Machine or Klima, and they have this. They're building a new climate model that has machine learning as its backbone for developing all their parameterizations. So you might be, maybe Vanda is familiar with this model, but yeah, it's just a major effort, of course, to do all that, and I think they're still learning about it too, so it's certainly not, I know some of the E3SM, they have calibrated runs, but it's for, as far as I was aware before, it was for very coarse resolutions that they calibrate. They say this model's calibrated for 2-degree climate runs or something. So if you want to run, a smoke plume or something, it's not set up for that really. So you're just running it out of the box. Yeah, so I think we're trying to push the envelope on the climate runs to mesoscale resolutions, where you're pushing them very high resolution to run them across the globe. And I don't think those climate models are set up for that. They're really, calibrated for large, multi-decadal runs or something like that. Whereas we're focused on sort of almost weather time scales really, but maybe short-term climate is what we're kind of looking at.
I think it's interesting you mentioned the climate model. There was a talk I recently shared with iHARP from Tapio Schneider.
Yes.
Marissa shared a couple of days, or maybe today. That was a very interesting talk, and that group does a lot of related work too. That might be interesting for folks.
Yeah, they have a big, their whole thing is this climate model will be built on, it's a new numerical method plus the newer numerical method plus all the parameterizations are going to be built upon machine learning methods. So you guys might have, I don't know if, but they're trying, I don't think they can do everything, because there's so many things in a climate model to parameterize. Like you might be able to contribute to the ice, for example, or something. You might be able to plug in there with them, aren't that?
Perfect. Great. Any other questions? Well, we're getting, yeah, go ahead, Sudeep.
I think like it's worth giving a try, like using the machine learning for climate model parameterizations now. Like we know the features like for particle size distribution number, humidity, and say we are finding a CCN number distribution or a particle size or droplet number distribution. And using linear and non-linear methods, maybe it's worth giving a try and see if that can improve the model parameterization in the future.
Yeah, I think I know at Los Alamos, they're continuing to do some of this work. This was just a paper I published as part of their project, but they had collected some experimental data, and like I said, NASA had a field campaign where they flew through the DC-8 aircraft through smoke plumes collecting, and so I mean, yeah, we'd have to think about if you guys still have interest in this thing, you might be able to see if there's any work we can do, or maybe a combined proposal on something related to that, that would use maybe some of that field data as well as your machine learning to kind of test some of these ideas. But that's something we could follow up on if you'd like.
Right, right. Like I was thinking, like DOE ARM has lots of data in Amazon over the Great Plain area. Then NASA has different campaigns like Seekers, different campaigns like forgot all the names. And so yeah, we can, and then we have climate model data too. So we can definitely follow up on that and think maybe a different way to parameterize climate models.
Yeah, yeah, and I have, like I said, I have these high resolution runs. If you're interested, if you find something useful in that, you could use the high resolution runs to calibrate, to run machine learning for the course runs, and then use to check on it. So but yeah, you could just shoot me an email, and although I'll be busy as a new professor here, I will follow up with you on ways we can collaborate. So
Sure.
It seems like there might be a lot of good collaborations following up. So good luck on the new start, Steve, and thank you so much again for a wonderful talk. I'm sure there'll be plenty of follow-up.
great. And yeah, you can use, so now I could send my UMBC email. That's the one I'll have for another year, I guess they give you after they cut you off. So someone can reach me at my sguimond@umbc.edu, and I'll slowly transfer over to the new one. So
Okay, sure.
Well, maybe I'll ask Marissa to just get your new email address as well, and then she can share it with some of us.
sure, that would be great. Yeah.
Awesome. Thank you so much, Steve.
Okay.
Hey,
Good one, everyone.
Thanks for the invite.
Thank you.
Absolutely.